Hello, I'm Yonggang Jiang from Nanjing University. I'm going to talk about the paper titled Trade-off in Contention Resolution without Collision Detection. This is a joint work with my co-authors Haimin Chen and Chaodong Zheng. First, let me introduce the model of contention resolution problem. In this model, there is a short channel, and there are several nodes or called players arrive over time. The time is discrete, and it is divided into synchronized time slots. So as you can see, a node can arrive in the beginning of some slots. Each node has a single message to broadcast. In each slot, a node can either broadcast or just be idle. If in a slot no nodes broadcast, then the slot is unsuccessful, of course. If there is more than one node broadcast in a slot, then they will collide with each other and the slot is unsuccessful. If there is exactly one node broadcast in a slot, then the slot is successful. And the node will leave the system immediately after it successfully broadcasts this message. An important thing is that nodes cannot communicate with each other. The only message they can get is from the channel. The channel will give the nodes feedback. The feedback is a binary bit. It is 0 if there is no success in this slot, which means there is no node broadcast in this slot, or there is more than one node broadcast in this slot. And it is 1 if there is a success in the slot. In our work, we also consider jamming. In real world, jamming is just like in a communication channel. The channel may be corrupt in some time, and which means at this time, no transmission in this channel will be successful. So as you can see, if a slot is jammed, then the slot is always considered unsuccessful, even if there is exactly one node broadcasting this slot, and the feedback will be 0. What I want to mention is that there is no global clock. So in the view of one node, when the node arrives in some slot, in its view, the slot where it arrives is the first slot. And its behavior in the second slot, third slot, etc. were based on the feedback from the channel on the first slot, second slot. And we want to devise an algorithm for the nodes. The algorithm is just about whether or not the node will broadcast in the ith slot, based on the history and the feedback before ith slot. So that's how we devise algorithm. Our goal is to achieve high throughput. Conventionally, throughput is defined to be the fraction of successful slots. So for example, in this case, there are 2 successful slots, and there are 5 slots that still contains some nodes in the system, so the throughput is 2 divided by 5. The question is, what is the optimal throughput we can achieve? Notice that if all the slots are jammed by the adversary, then we can only achieve 0 throughput. That is trivial. But what is interesting is that if it is guaranteed that some fraction of the jammed slot will be jammed by the adversary, like there are constant fraction of jammed slot that can be jammed, then what is the optimal throughput we can achieve? In our paper, we answer this question by giving an algorithm and prove the tight lower bound for the algorithm. I give some examples to explain the result of our work. For example, if the adversary is guaranteed to jam constant fraction of slots, then the best algorithm we can achieve is 1 over log n throughput. And if such a fraction of slot can be jammed by the adversary, then the best algorithm we can achieve is actually constant throughput. And in general, for any function g, if 1 over g fraction of slots can be jammed, then the best algorithm can achieve such a throughput. This is a function depends on g, so that's the most general results achieved by our work. Before I explain the results of our work, I want to talk about some previous work. Many previous work in contention resolution adapts the ability of collision detection. If the nodes have collision detection, then the feedback is no longer binary bits. It has 3 types of feedback. If the feedback is 0, that means no nodes broadcast in the slots. If the feedback is 2, that means there is collision happens in this slot, and that's why it called the collision detection. And if it is 1, then that means the slot is successful. If the nodes had the ability of collision detection, then there is a very simple strategy. That is, if the nodes get the feedback of 2, that means too many nodes stand in this slot, and the nodes just simply decrease the probability of broadcast. And if it gets feedback of 0, then the nodes just increase the probability of broadcast. And that simple strategy is proved to be very efficient by previous work, and it can also tolerate jamming. I put some previous results here and show how we improved their results. In a recent paper, they give the first algorithm that achieved constant throughput without collision detection, but their algorithm cannot tolerate jamming. In a previous work, they give a constant throughput algorithm with collision detection and can tolerate jamming. Our work are in the setting that without collision detection and with jamming. We close the gap of this problem by proving both upper bound and lower bound of this problem. The rest of this talk will focus on the algorithm and how to prove the lower bound. Our algorithm is based on a recent work that gives the first constant throughput algorithm without collision detection. In their work, they proved that the contention resolution problem can be reduced to 2 facts, or to say to simplify the version of the problem. But the 2 facts is not correct when they are jamming, so we will propose our new changed algorithm and show that in this changed algorithm, the facts will tolerate jamming. The fact is correct even if there exists jamming. First, I want to show a very useful technique to solve contention resolution problem, that is exponential backoff. There are several descriptions of it. I put the very easy description here. That is, each node just broadcast with probability 1 divided by I in the ith slot after it gets into the system. That means the node runs an exponential backoff. Why exponential backoff is so powerful? Let's see this example. Consider the situation when there are n nodes arrive in the first slot, and let's compute the contention of each slot. The contention is defined to be the expected number of nodes that broadcast in this slot. So, since all nodes broadcast in the first slot with probability 1, the contention in the first slot is n. And the contention in the time slots half of n is 2 is a constant. With standard analysis, one can show that if the contention in the slot is constant, then the probability that the slot is successful is also a constant. And actually, in the interval half of n to n, all the slots has constant contention, which means all of them has constant probability of successful. That means there are theta n success happens in expectation, which is very good. So that's the power of exponential backoff. However, we do not consider the case that there may be other nodes that arrive the system and disturb those slots from success. Actually, if there are new arrived nodes that in the system, then this factor is not always correct. But in a recent paper, they proved such a fact. Let's consider a simplified version of this problem. That is, the new arrived nodes, the additional nodes, will leave the system upon see a success. Note that this success is not the success of these additional nodes, but the success feedback from the channel. So when the channel gives them feedback of success, then the additional nodes will leave the system immediately. In this simplified setting, the power of exponentially backoff is still correct. That is, in expectation, theta n successes will happen in this interval. This fact is still correct even there are constant fraction of jamming. That is reasonable, since constant fraction of jamming can only jam constant fraction of this interval. And the rest constant fraction of this interval will still contribute theta n successes. Now let's see fact 2. I want to mention that the exponential backoff is powerful if all the nodes is guaranteed to arrive in the first slot, but it is not powerful that it will not generate ZN successes if the nodes arrived arbitrarily in an interval. So if the nodes arrived arbitrarily in an interval, there will be not many successes. But what is guaranteed is that there will be at least one success with high probability. That is what the fact 2 shows us. However, fact 2 is not correct with constant fraction of jamming. Let's see why. Consider the situation that one node arrives in the first slot and run the exponential backoff, and the adversary will jam the first half of this interval. Now, the node will broadcast with probability, a constant divided by n, in the later half of this interval. And with standard analysis, one can show that the node will successfully broadcast in the interval with constant probability. But in fact 2, we need the node success with high probability n, so fact 2 is not correct if they are constant fraction of jam. Let's see how to solve this problem. We slightly change the exponential backoff. Now the new exponential backoff will not send with probability 1 divided by I in the ith slot. It will send with probability log I divided by I. It is a slightly higher probability. Why this is powerful? Let's see the previous hard case. That is, one node arrives in the first slot and the adversary jams the first half part of this interval. And now, the node will send with probability log n divided by n in each slot in the later half of this interval. And one can show that the node will success with high probability with standard analysis. And actually, I set the numerator to be log I because here we consider the situation that they are constant fraction of jamming. If the jamming severity is changed, then we can also change the numerator to be other function that depends on the severity of the jamming. So that's how to expand this to a general case. So here is the new fact 2 that can tolerate jamming. We can show that with our new changed exponential backoff, and n divided by log n nodes arrives arbitrarily, at least one success will happen with high probability. Now let's go back to see fact 1. We also need to slightly change the description of fact 1 because now the new arrived nodes, the additional nodes, will run new exponential backoff. But notice that the synchronized nodes in the first slot will still run the exponential backoff. And we can prove that in this setting, ZN successes still happens in those slots even with constant fraction of jamming. To summary, let's put the two facts together. The remaining problem is how to reduce the contention resolution problem to the two facts. I want to focus on this because it is the same as the recent paper. Basically, they use fact 2 to generate at least one success and use this success as a signal to do a synchronization for all the nodes that's injected in the previous phase. And those nodes will use fact 1 to generate enough successes. And that's how it works. Now let's focus on proving the lower bound. Actually, we will prove a much stronger result. That is, in an interval of length t, there will be no success if at least t divided by log t nodes arrives in the interval. And that is a stronger result because if there is no success, then the throughput cannot get to like 1 divided by log t. And why we need this stronger result? Actually, it has some advantages. Just imagine, each node that arrived in the interval will see no success until the end of the interval. And since their behavior is totally based on the feedback of the channel, and the channel always gives them the same feedback, that is 0, so their behavior will be the same. That is, they will broadcast with the same probability after they get into the system in the first slot, and broadcast with the same probability after they get into the system in the second slot, and etc. And that will help a lot in our analysis of lower bound. With this argument in mind, we can discuss the total expected broadcast time of one node in the first T-slot, if it never sees any successes. That applies to all nodes that arrive in the interval because we assume the interval contains no success. And we will discuss if it is too small what will happen, and if it is too large what will happen, and use this to make a contradiction. If it is too small, that means one node will broadcast very small times in the interval. And just imagine the adversely strategy that inject one node in the first slot and then perform some random jamming in the next several slots to prevent the nodes from success. Then since the node will broadcast with very low probability, it is hard for it to successfully broadcast its message. If it is too high, then that means each node will broadcast many times. It will broadcast with high probability. And just consider the adversely strategy that injects as many as possible nodes into the interval. And one can prove that by injecting those nodes, each slot will have a very high probability of collision. With high probability, all slots will be collision and there will be no success. And that will lead to a contradiction, and our lower bound is proved. Note that this proving technique is also from the recent paper. We slightly changed their idea and get a lower bound to perfectly fit our upper bound. What is surprising is that this slightly change just closed the gap of the condition resolution problem without collision detection and with jamming. And that's all it contains. Thanks for listening to the talk.